Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Human problem. And also there's certainly a lot of issues with binding. What is the precedence of this? If I say go to the market and get something that's not an apple or a pear, you came back with a pear, I'd be annoyed. But of course that's perfectly fine in computer languages because not binds with apple and not with pear. Arithmetic was often done in natural language style. People seem to be thinking of their data more like lists than like arrays, in the sense that they don't make room for stuff, they just stick things in and expect it to expand by itself. Objects have, the entities that people talk about have object-like characteristics in the sense that they remember stuff about themselves, they remember their activities and their data and things like that. So you can talk about Pac-Man as an entity and what they should do. So those are some of the, just a few of the results we had. We used these as a way of designing a new environment that was primarily aimed at kids. Had a bunch of other interesting properties that the data was presented on cards, so all the data was always visible. It wasn't invisible data like in most systems. Got Andy, which is this little doggy here, is the person who's kind of executing your program, and you can click on him to see his thought bubble, which is the actual code. The code is kind of a natural language style, like AppleScript or Flash, things like that. And there are some domain-specific operations that are useful for animation, like moving things and so forth. And anything that you can do in singleton, you can do on sets, so there are queries to return sets of objects. So you can say set Buzzy's direction to 90, which does 1B, but you could also say set all B's to 90, or set all B's who are above 20 or some property like that. And that would work exactly the same way. And there's a video online if you want to see more about it, but I'm going to move on to more new stuff. So what we're doing now, moving on from the language, is looking more at the programming environment, looking at tools that are equivalent of Visual Studio or Flash or things like that. And look at, can we use the same methods about studying programmers, studying what people do, as a way of improving the programming process for whatever language you're using, whether it's C# or Visual Basic or Flash or anything like that. And again, we're taking the same steps. We're studying what people do. We develop systems inspired by the observations of what people do, and then we try and evaluate the results to make sure we're there. And in this work, we're targeting both novice and expert programmers, end-user programmers, novice or beginner programmers, students, and professional programmers. And we have about 5 studies, 1 new tool, lots of new ideas, and you'll see kind of the talk kind of ends right in the middle because we've done all these studies, we've got all these great ideas, and we're right in the middle of trying to implement them, see if they work. So the first thing we did was studied some people in the Alice environment, which was done by a colleague of mine, Randy Pausch. And it's basically a toy programming environment for doing 3D animations. And we liked it because it uses a drag and drop style. So if you want code, you drag it out of here and drop it into the code window. And if you want to edit it, you kind of drop it out. The advantage of that, of course, is you can't make syntax errors. So a lot of the kind of errors that a beginner programmer would make are gone. And an expert programmer using this can program a substantial amount of code fairly quickly. If you know anything about syntax editors, it's really good for creating code quickly, and it's really terrible for maintenance, really terrible for editing. Okay, but we were doing pretty much a study of creating code, and so that kind of had a good trade-off. So the advantage was in a 2-hour study, we could see lots of stuff happening. Whereas if you took on a beginner and C# environment, in 2 hours, nothing much would have happened. Alice is optimized for creating 3D animations, and there are all sorts of other things that it protects against. The other nice thing about Alice, of course, is we could get in there and change the execution model, change the code, because we had all the source locally and a lot of expertise. So we studied, did we say what we studied? Oh, yeah, 3 experts and 4 novice programmers over the course of about a month, and almost 900 minutes of observations. And there were lots and lots of problems, as you might imagine, not very surprising. And we defined breakdowns as situations where the programmer was confused about what happened. 102 of these caused errors. A lot of the errors went to more errors. And in fact, that was one of our interesting findings, is that there were often these long chains of breakdowns where somebody would make an error, they would try and fix it, that would generate more errors in the code. And in fact, the average chain had 2.3 breakdowns. So almost every case when there was an error, it caused at least one more error down the line.
Is the 33 included in the 102?
Yes. Overall, almost 50% of the programmer's time was spent during debugging, and this is in spite of the fact that the compiler was, there was no compiler step, and that all these other kinds of errors were eliminated. And the tasks were fairly simple. And the neat thing, well, just to focus on this some more, we took all of these observations of all these errors and classified them into different categories. Yeah, Rob?
So from the previous slide, can you say a little bit more precisely what debugging means? What did you count as debugging, as opposed to what were the other activities? What's the other?
Yeah, we'll get to that. You'll see. You'll see in this, basically we have this model of all the things that breakdowns happened and all of the activities that people did. And we classified the problems into 3 different groups. Knowledge problems, which is when they didn't know something. Attentional problems, which was when they kind of did something wrong. And strategic problems are when you kind of don't know how to do something. And so we developed this model of all the things that happen. And so you have breakdowns that can be a knowledge problem, an attentional problem, or a strategic problem, and that repeats in all these. In the specification time, the implementation time, or debugging time. And implementation problems can lead to errors. Errors can lead to faults, and faults can lead to failure. So an error is when you make a mistake in the code. A fault is a faulty data inside the code somewhere. And a failure is when it's something on the output that you actually notice. And so sometimes you don't notice. Sometimes there's more than one error that causes fault and things like that. So here's an example. They were trying to check in a Pac-Man game when all of the dots were eaten. Okay, and that's kind of tricky Boolean logic to create, and so they created it wrong. And so they had trouble creating the Boolean logic because they didn't really know how to do it. And the result was that they implemented it wrong, and they actually made 2 different errors. So errors look like this. So they have 2 different errors in the code. The effect was that the conditional came true before it was supposed to, and Pac-Man bounces before all the dots were gone. That was the effect. And so then they tried to figure out why that happened, but they made an error in figuring that out because they couldn't really tell what was going on, and so they modified the wrong thing. And as a result, they added a new error, and so on. And so they actually made the code worse, and it goes on, and eventually they give up. But
how would this have been different, bigger probably, your model, if they had been allowed to make all the other kinds of errors that were being prevented from the toy environment?
Yeah, so there probably would be more, lots and lots more problems in the implementing section, because they would have made all these compile time error kind of things, syntax errors, and they basically, would be making zillions of those, and basically just slowing them down.
But you haven't augmented this based on expert programmers' behavior yet?
No. We basically just kind of use this as a way of analyzing this particular study and motivating the next one. But it's certainly out there if somebody wants to look at what it might be useful for. And another thing that we observed was that all of the debugging problems that they had. I'm sorry, Rob, did that answer your question? Or
I think so, yeah.
basically, they spent a lot of time trying to figure out what happened, and that's something else we'll get to. Is they were trying to figure out what algorithms to write and that kind of thing. Were you asking what happened?
So your colleague Bob Harper has this funny phrase about students. They like to debug programs into existence.
Right.
And so I'm trying to account for this 46%. Like how much of, so presumably a bug is any deviation from the spec they were given, like what they were supposed to accomplish, right?
Well, it was actually what they had in mind to do at that particular time.
Right. So I'm trying to get a feel for how much of this 46% I would actually think of as just sort of creating the program, trying to get it to do any little thing and then build upon that to get it to do the thing I really want.
Right.
And how much of that is, chasing down things that are obvious bugs, right? Like something doesn't show up on the screen.
Right. I think in this time, well, if you're trying to divide the 46% into what are the different aspects of that, that's what the models were supposed to do. The other 54% of the time was spent, reading the specification and typing in stuff and dragging and dropping and that kind of stuff. So pretty much from as soon as they started running the code and discovered it didn't do exactly what they had in mind, that's when this clock started. So the interesting thing that we discovered that wasn't much surprising to me, but was surprising to Andy, was that virtually all of the debugging sessions, debugging issues, could be answered by why questions. Why did this happen? Why didn't this happen? Why is this object not moving? A little surprising was that almost over two-thirds of the questions were not questions. Why did something not happen? Okay, which, as you may know, today's debugging tools are particularly, inappropriate for answering. You put a breakpoint and sure enough, it's not reached. That was helpful. So our thought was how we could enable people to directly ask why questions in the user interface itself, in the programming environment. And then, provide answers in terms of the code and the execution history. Why do we think we can do why not questions? Well, that's because people, even though some of these were novices, did not expect their code to do stuff that they hadn't written yet. Okay, so they weren't that novice, So they only really asked why not questions about things that could have happened, code they wrote but wasn't executed for some reason. And so that's something you can analyze, right? They didn't ask, how come I'm not being served dinner? Because they hadn't written any code for that. And the way that we're implementing this is that behind the scenes, every single action is being logged, every single variable being changed, every execution call. And then we're doing what's called slices along backwards chains from the place where the code stops to look at causes and things that either happened or didn't happen. The answers use a text message, a visualization we call the Y-line, which shows both data flow and control flow that lead up to certain situations, and then highlighting of the code and data that's relevant to whatever being talked about. So let me run the video.
The Y-line is a new debugging tool that lets programmers ask questions about their program's output and behavior. We have prototyped the Y-line in the Alice programming environment, which has been designed to help create interactive 3D simulations and animations. Alice supports a drag-and-drop interaction technique for editing code, which prevents all syntax and type errors. We'll use this Pac-Man program to demonstrate the Y-line. We'll go through 3 examples of how a programmer we'll call Ellen used the Y-line to help her implement various parts of the game. In our first example, Ellen is trying to make Pac-Man move forward like this. First, she clicks on Pac-Man in the object list and creates a new method called movePac. This will execute all of Pac-Man's animations as the program runs. She then drags a move animation to the movePath method and chooses forward 3 meters per second as parameters. She then tests her program by pressing the play button, but Pac doesn't move. Programmers typically respond to this type of failure by asking, why didn't Pac-Man move? They came up with several possible explanations. On average, it took programmers 2 to 3 minutes to diagnose this failure. With the Y-line, however,
So quick, why didn't it work? Anyone else? I think it.
The failure is quite simple. She clicks on the Y button, which pauses the program and brings up a hierarchical menu of why did and why didn't questions. The why did menu is generated from all of the changes to output that were executed while the program is running, and the why didn't menu is generated from all of the possible changes to output in the program, whether or not they executed. Ellen chooses why didn't pack move forward 3 from the menu, and as she does so, the corresponding output statement is highlighted in the code editor. The Y-line's answer indicates why pack move forward never gets executed. It says that the move statement only happens when the move pack method happens, but nothing makes move pack happen. This is an example of an invariant answer in which some output statement always or never occurs. To fix this error, Ellen creates a new event to call move pack while the Alice program is running. She then tests the change and Pac-Man moves as expected. In our second example, Ellen wants to make Pac-Man shrink if he touches the ghost, as shown here. To do this, she creates a do-together statement, which executes multiple statements concurrently. She puts the animation inside of it. She then adds an if statement, which checks if the ghost is within a certain distance of Pac-Man. She does this by using one of the ghost's questions, which is called is within threshold. She guesses that 2 meters should be about right. She then drags a resize animation, so that if Pac-Man is close enough to the ghost, Pac-Man will resize to nothing. She indicates this choosing a resize factor of 0. When she tests the new code, Pac-Man clearly intersects the ghost, but doesn't seem to resize at all. Ellen asks, why didn't Pac-Man resize to 0? The Y-line answers by saying that Pac-Man did in fact resize, and it shows a visualization of the events that happened at runtime that caused him to do so. This is an example of a false proposition answer. The question that Ellen asked implicitly assumed that the resize did not occur, when in fact it did. Note that even though the resize did occur, she was still able to find this question in the why did menu. Allowing questions with false propositions allows the Y-line to reveal programmers' false assumptions about their program's execution. Ellen can drag the time cursor in order to scrub through the execution history and see that Pac-Man did in fact resize as a result of the is within threshold expression evaluating to true. Because the Y-line helped Ellen limit the failure to the resize statement, she decides to try a non-zero parameter. Ellen then tests this change, and Pac-Man resizes as expected. It turns out that in Alice, resizing to 0 has no effect. In our final example, Ellen wants to prevent Pac from shrinking if he's eaten the big dot, as seen here.
Has anybody ever found something like that in a Microsoft API? That some interesting parameter controls something you didn't expect.
In our final example, Ellen wants to prevent Pac from shrinking if he's eaten the big dot, as seen here. To do this, she adds another if statement to the do together. This will test if Pac is within 1 meter of the big dot. If this becomes true, it will set the big dot's is showing property to false, which will cause it to disappear on screen, and indicate that it has been eaten in the code. She then elaborates the ghost collision conditional to prevent Pac-Man from resizing if the big dot has been eaten. Ellen tests the changes, but notices that even though Pac-Man obviously eats the big dot, he still resizes when he touched the ghost. Ellen simply asks, why?
Okay, any theories? It's actually a very complicated...
Why did Pac-Man resize? In this case, the Y-line shows all of the control and data flow actions causing the resize to occur, including the if statement and the expressions evaluated as part of the if statement. As Ellen selects different events in the visualization, the code corresponding to the action is highlighted automatically in the code editor. Once Ellen notices that big dot is showing was true when the conditional was evaluated, she says to herself, wait, I saw the big dot disappear. This shouldn't have been true. She then asks, why didn't big dot is showing change false in the context of this question? The resulting visualization combines the results of the two questions and explains that big dot is showing did change to false. Alan traces backwards from the resize, noticing that the two conditionals were interleaved. The second conditional began to execute before the first conditional was complete. To prevent this interleaving, she stops the program and moves the big dot collision test before the do together to ensure that it gets executed before the other test does. Pac-Man becomes invincible when he eats the big dot, as expected.
This was a multi-process kind of...
In user studies comparing Alice with the Y-line to Alice without the Y-line, the Y-line decreased debugging time by an average factor of 8 and helped programmers complete 40% more tasks than users without the Y-line in the same amount of time. We are currently investigating ways to extend the Y-line to more professional programming languages and environments, and even to desktop applications such as word processors and email clients.
So just to reiterate the really dramatic results that we got, is that we had a factor of 8 speed up in debugging time and significantly more reliable code because people weren't adding extra errors into their programs as a result of trying to remove other errors. And as a result, their overall programmer productivity was about 40% higher. So that's really exciting results, and we wanted to see, does this technique scale up to professional programming environments, C# or Java or whatever. And so the next step was obviously to rebuild the Y-line into a professional environment, but along the way we got sidetracked by lots of other questions, so we still haven't answered that one yet. That one's still pending.
Just a quick question about the design of the Y-line.
Mm-hmm.
So one of the things I find interesting about it is you have two representations of the program, right? The one in the middle is actually like the source code, as it
Right.
were. And then the one at the bottom is a concrete execution.
Right.
So this creates for the programmer a kind of correspondence problem. How do I figure out what a bubble or a moment in time there corresponds to the one in the source text? Because that's where I have to change the behavior. Right? So it seems like, I guess, for your users that wasn't a big deal.
Well, we did a lot of work. As you notice here, this guy is selected, and the equivalent piece of code is selected. So, and also, if you notice, when you click on the Y menu itself, it actually highlights the code that corresponds to each line there. And we found actually that sometimes people didn't even have to ask the question. They could just look at the menus. And by being able to ask the Y questions and seeing what code was highlighted, sometimes that was even enough. Because the code here is coordinated by color, if you notice, it's the same color. It's coordinated by name, so that it uses the same terminology. It graphically looks the same, uses the same terminology, and anytime you click on something, it moves the code to the right place. We didn't see that being a big problem. What was a big problem is that code that's executed a whole bunch of times, you'd end up with a long string of them, and then it's tricky to figure out which one you're talking about.
The point you made about looking at the questions is an interesting one. I just wondered if you have any insight about the ability for the users of this environment, or perhaps in the professional programming environments, the ability of people to ask the right question.
Well, one of the key issues about scaling up, right, is to what extent we're going to be able to make sure their questions are in the list, right? And we found that about 95% of the time, the questions that they wanted to ask were indeed in the list. And, all of the questions, well, our observation was that people wanted to ask questions about the output, about things they saw in the environment, because this was a highly graphical application, and the behaviors they want were all expressed graphically, and so it made a lot of sense to ask about things that happened in the scene. And usually, it wasn't a problem knowing what they wanted to ask about, because they wanted to ask about why something didn't happen in the scene. When you scale up to a professional environment where things are more hidden and you're talking about internal stuff, and it'll be more interesting to see if we can have the right questions in the menus. The times when the right questions weren't in the menus were cases where the Y-line really wouldn't help because they had designed their Boolean logic incorrectly. And so sure enough, they knew this piece of code had executed, and they knew it was wrong, but they didn't really know how to fix it. So those are the kind of things that this really isn't designed to help with. But I think the challenge is getting the right questions in the menus rather than having the programmer recognize the questions when they're there.
Has there been any examination as to how this might scale to a more layout-driven programming environment like Avalon that's kind of data-driven, and people are now trying to figure out how to debug a hierarchical layout of things that are relatively connected to each other visually?
Yeah, that's more of a constraint debugging problem, and we've done other work not related to this that really looks at more debugging of declarative things like constraints and things like that, visualizing data flows and that kind of stuff. A colleague of mine, Brad Van der Zanden, had an interesting tool about that a few years ago. But that would be interesting to think about, exploring how that connects with this, because certainly this data flow kind of thing is useful. Margaret Burnett at Oregon State has done a bunch of stuff with spreadsheets, which are very similar to data flow kind of things, where it's all about constraints and layout. Is all about how the values go from place to place. I think that would be an interesting thing to look at to see if that the same visualizations would work, or whether you want to do something else. But I think in terms of the concept, that what you want to ask about is things that happened in terms of layout. Why is this here and stuff like that, is really interesting. And we're doing some current research this summer to look at focusing the questions based on being able to point to stuff. So if you could say, why is this here? Then that would really help with making sure the menus have the right things in there. Okay. Another study we did was looking at more on learning. It turned out, coincidentally, at the same time, I was teaching a class on HCI to a bunch of people who didn't know how to program, and they were learning Visual Basic and Flash during the course of this course, and Andy was one of my TAs. And so we took advantage of that to do a bunch of studies of the problems they had and try and reflect on what we could learn from that. Looking at the prior literature on learning, there was an enormous amount of work on how people learn to program done in the early 80s. And but surprisingly, most of it was about programming language kind of things, what syntax people have trouble with, and what sort of for loops and stuff like that. Virtually nothing about the editor, debugger, the help system, the error messages, all this kind of stuff that's really a big part of the environment. So we looked at all these kids trying to learn VB.NET in my course, and we looked for what we called insurmountable barriers, which is basically where they got stuck and had to ask the TA for help. We did all sorts of coding of what they asked about and what the problems were and things like that, and looked for what we could learn from the kinds of things that they were stuck on. And of these, we sampled 130 barriers from about, almost half of the students. And a lot of them, they seemed like they were able to overcome them themselves, but they actually overcame them wrong by making false assumptions, which then ended up getting them stuck on something that, So I thought that I could do this, and then I got stuck. So that's this group here. And then we kind of classified them and stuff like that, and did the usual stuff. And we came up with a set of 6 barriers. I'm just going to talk about a few of them. There were a lot of design barriers where the students just didn't know how to program something. How would I actually make this work? And they didn't know how to write a sort algorithm. So it really wasn't very surprising that they got that all wrong. They didn't know how to do concurrency. Boolean logic, again, showed up as a problem. And to solve this, well, you have to allow them not to do it, right? There's a built-in sorting algorithm. Why should they write one? And, so anytime you can eliminate having to do some of these kinds of things, then you're really helping your novice programmer. But the problem is, of course, this leads directly into the next problem, is as soon as you provide a sort routine and so forth, then they have to be able to find it. And so the selection barriers where there must be something that does this, how do I find it? Or I don't know it when I see it, how do I recognize it? Maybe I'm calling it the wrong thing. How do I use it when I found it? And a very robust finding that also is true for experts is that when you don't know how to do something, finding an example is much easier than finding a whole bunch of documentation. So here's a good example. One of the tasks was to keep time on a clock. And so they went to MSDN and typed in time, and they got 500 results. And that wasn't particularly helpful. And sure enough, almost all these have something to do with time. But which one do I want? This is basically useless. Might as well give up at this point. And it doesn't seem to be ordered in any kind of interesting way. So after they found something they wanted to use, they've overcome the selection barrier. Now they have to know how to use it. But that's also hard as well. What actions can I do with this? How do I set them up? What effect will these actions have? And this is both in terms of programming language constructs and the APIs. There really wasn't a big distinction in the user's minds between, a do loop and the time function, right? Because both of them are things they have to learn how to do, and they have certain requirements and that kind of thing. So this distinction that computer scientists have always made between the language and the APIs and the libraries really isn't very appropriate in terms of how people learn to use these, because they have to learn them all at the same time anyway. And then another thing that was really hard was that I've got these two things, and they kind of work okay. I kind of understand them, but how do I make them work together? And we call those coordination barriers. And there are all sorts of rules in all of these environments. This has to be called before this, and you can't do this. And this is true across all the APIs. We saw this with the experts as well. Of course, they try to guess, and they're almost always wrong. Here's a good example. If you have two forms in VB, there's no way to get data to a form that hasn't been instantiated yet. Okay, so if you try and push data, you get null pointer exception. It has not been shown, right? Or if you try and, I forget which way it goes. But anyway, if you have multiple forms, what do you do? Well, you have to use global variables or something like that, because it's really hard to pass data around. Also, there are all these language constructs using languages, data of different types, and all sorts of other examples. And then there are understanding barriers, which are no surprise from our Y-line study, that, what happened? Why did this happen? Why didn't it happen? They added a timer, but it didn't seem to do anything. Why not? So exactly the kind of things that the Y-line we already showed was good for. So we took all of these ideas, and we were thinking about re-implementing the Y-line for professional designers, professional programmers. Meanwhile, James Fogarty, another CMU student, wanted to do a study of interrupting programmers. And so this all came together really well, and we decided to do a study of how expert programmers, could perform a maintenance task. What were the actual steps that people did? And we're really focusing now on kind of minute-by-minute maintenance tasks. Okay, so we're not talking about the architectural design or the global design or all the kind of big software engineering things. We're really talking about I need to change this feature. What actual code do I fiddle with and things like that. So it's an entirely different level than most of the previous studies have been looking at, and we're looking at all the interaction techniques around the environment. And I'm really proud to say that Andy won the Distinguished Paper Award at ICSI last week with this result. So we took 10 expert Java programmers, self-described experts. We didn't actually verify that they were experts, but they probably were. We used Eclipse. The program, we gave them 5 tasks to do, from fairly simple to fairly difficult. We paid them $10 for each one they completed, so they were motivated to complete them in any order. And they used kind of the standard tools for documentation, Java docs, the internet. They could use Google to search for examples and so forth. And we gave them 70 minutes, and they could do as many as they could. We did screen capture videos, and about every 3 minutes we interrupted them. This really helped end James's result, which he won a Best Paper Award at CHI, and Indy was second off on that. But it's surprising that, in fact, data shows that for real software engineers, this is realistic, that a real program is going to either interrupt himself or be interrupted by somebody else pretty much every 3 minutes with some other task. Email comes in, an IM comes in, the phone rings, we decide to take a walk or whatever. And so it's fairly realistic. And in addition, we were very interested in what programmers do to remind themselves about what they were doing. And what sort of tools do programmers use to keep track of stuff, and in this way we can really try and build some of those into the environment in a better way. So the paint application, a fairly small program. It's only 500 lines. And it could do certain things, but there were 3 bugs and 2 new features that we asked people to work on. So we got these 10 videos of people, and we had 2 different experts encode them at a fairly fine level of detail, and we got hundreds of, this is really laborious work. We labeled every user interface action in the development environment itself, every navigation the people did when they were reading code, when they were switching amongst environments, when they were testing, so kind of every little action that the user did minute by minute. And here's how it broke down on average. They spent about 20% reading, about 20% editing, about 20% navigating, 13% trying to find new code that would work for them, looking at the API, testing. So, fairly little time testing. Most of the time was trying to figure out what was going on. And we could break down the actions. This is one programmer's actual data into various stages. So first they were trying to figure out what's going on with this code. So this is code they're not familiar with. They have to figure out what part of the code is relevant. Then they're navigating within that to really understand it in more detail, and then finally they're editing it. We call this forming a working set. At ICSI we discovered people now are calling this concerns or something like that. Then they're navigating dependencies within that, and then finally they're doing a modification. So, and of course these overlap in time. So here is all 508 lines of code, and the interesting thing here is a working set for one particular application is spread throughout all the files. Is this a bad design? In fact, no. That fundamentally in all modern programming environments, you're required to spread out your code for new features, throughout the code. Imagine you're making a new button, and the new button goes in one part, the callback for that button goes in another part, the actual action it does. You're using model view controller, you have to add something to the model, you add something to the view, you add something to the controller. So there's pretty much fundamentally required that anything you do is really going to touch code in lots of different places. So the first step was trying to form the working sets. How does this work? And they're trying to find in the code which pieces do some tasks that they've seen happen in the user interface. And they'd often make up words or think of words. Maybe this is called pencil. Let me search and see if I can find pencil. But only about 50% of their searches actually led to the code that was relevant to that, because the programmers weren't that good at guessing what the words might be called. For dynamic things, they would look for why things didn't happen, and they'd form hypotheses about what part of the code was causing that, but most of the time they were wrong. And so the result, of course, is that people have a hard time finding which code is relevant to a particular task. Then they want to represent the working set so that they figured out now all those little pieces of code that we saw in the picture that are relevant. How do they keep track of that? Well, you have tabs in Eclipse where you can have little files open, and there's something equivalent in Visual Studio, I'm sure. And then there's the browser. This is the object browser, or the method, inheritance browser. And then they would open, often, the files, the objects that they wanted to deal with, and try and use the fact that they're open as a cue that this was what they were dealing with. But of course, this is fairly inefficient. The more you get open, the harder it is to read them, the harder it is to keep track. And this is by file, and often it's 2 or 3 lines in that file somewhere, and so then you lose track of that. And of course, if they got stuck on one of their tasks and decide to switch to another task and come back, their working set is all messed up. So what about navigating inside a working set? There were about 65 different dependencies that people navigated on average. So this was a very common thing. They would spend a lot of time going back and forth, from a call to its definition, from a variable to its use, things like that. About half of them were direct, that Eclipse actually has built-in commands for each of these kinds of navigation, if you happen to know what they are called, or can find them in the context menus, declaration of, use by, called by, definition of. But on the other hand, about half of them were indirect. Find the method that computes the value that's passed to this method that then I'm using here. And of course, there's no way to do that without, typically scrolling around and so forth. And in a modern environment, you still spend an enormous amount of time navigating around to find all this stuff. And each one is fairly quick. And so if you ask a programmer, what's the hardest thing about using Eclipse? They're not going to say, I spend too much time scrolling. Right? It's not something that people have consciously in the front of their head. And I think this really comes to the fact that it's not sufficient to just ask programmers to introspect about where they're losing all their productivity, about why aren't you programming faster. Okay, they spend 35% of their time scrolling around, in some sense needlessly. Okay, if you ask somebody, are you wasting a third of your time scrolling around, they're probably not going to say, yes, that's exactly what I need you to fix. But in fact, when you do an analysis of this level of detail, you can see that this is really a big time waster for people. And so this is something that we're thinking about addressing. And how might this work? Well, programmers could explicitly grab arbitrary fragments. As you grab a fragment of code, it could automatically bring in the dependencies, what's called by this, where the declarations are. Put them all in one place and show dependencies among them. Support multiple working sets, so you can say, save all this as a unit. I'm going to call it, task 1 or, the paint task. And then, so you can switch back and forth. That would be really trivial. Of course, integrate with the Y line, so if you ask about something, it can bring in all the relevant code into a working set. And then, allow people to prune. And we've done a painting of what this might look like. This isn't real, obviously. This is just a painting. And when we presented this at ICSI, there was a lot of concern about whether this would scale up to real programs, and that's obviously something we're looking at. But this is a working set for one of the tasks that we had people do. We have copy and paste, and there's all sorts of stuff that's highlighted. They're looking for B slider here and things like that. And there's a different multiple working sets that you can switch around to with a single click. So it's basically just a concept of how you might take advantage of this knowledge about what people are really spending their time on to build a new environment.
So one of the things we saw in our study of programmers, which I think I just heard you say, is that people would basically open new files and get new tabs. Mm-hmm. And they would not do fine-grained maintenance of that. They would not close just certain ones of them that they know they
right.
would need. They would basically open until they get overwhelmed, and then they'd close them all and they'd start
right.
again.
Right.
So this makes me concerned that programmers don't want to spend time doing
yes, exactly.
to maintain their working set.
Right. And so if you see a lot of these ideas are basically you start from someplace and the rest is done automatically. And so that's a real interesting question, is to what extent can we tell from operations like, this is what I'm interested in, or starting from the Y line and saying, here's the piece of code that's relevant to this thing I'm doing now. Can we generate a lot of the rest of this automatically? And I think that'll be a really interesting thing to look at.
It would be interesting to see as we increasingly move into this more integrated development world where we have a Visual Studio team system or something like that, where we also have our bug tracking also in the form of track that along with the working sets that we use.
Yeah, that'd be really interesting.
When we come back into a bug on a section that we've used before, we can say, well, maybe we need the same working set because it looks like it's the same kind of bug as we have.
Exactly. And I think there's a lot of advantage to saving these. Here's what I used when I was fixing this problem. And I think, there's no reason that CVS kind of thing shouldn't save this along with the other kinds of stuff that you're saving in order to keep track of what code was affected.
You see any indications of individual differences among programmers that might turn out to be?
I don't recall. I mean, I'd have to ask Andy that. I don't really know. That's a good question. There's a lot of results. There are top-down programmers and bottom-up programmers and all this kind of stuff. So you would certainly imagine there would be. And I don't really know to what extent that affects this kind of behavior. I mean, there was definitely, now that I remember, there was definitely, some programmers who like to kind of go through and understand everything before they started working on stuff, and other programmers who would, fiddle at the local level. But I don't see any reason why this kind of tool wouldn't be effective for both. And you might imagine, to the extent that you could, to have the tool encourage whatever kind turns out to be more effective, getting a bigger overview first.
I was just going to say, in the Visual Studio, we do see 3 different types of programmers, and we see them when they're working on forming these working sets. Mm-hmm. The difference in behavior you see is the scope to which each different type of programmer, the scope in which they look for things that encompass within that working set. Some programmers just look for things that are in the file that they're working with, or maybe a couple of files in their own project. Others go way out beyond that. There are definite differences in behavior forming these working sets.
Okay. Now we have this big videotape of all these professional programmers doing stuff, and we've used it for 2 more studies. The same, got this rich set of encoded data. One was looking at how people learn APIs, and it turns out people much prefer to go to examples than to use the documentation. And in fact, people often use Google instead of MSDN or Java Docs in order to search. And why is that? Well, a lot of it has to do with the vocabulary problem. People are trying to get this thing to fade out. So they look for fade out, and sure enough, they find sound stuff. Right? And so they look for transparency, and they don't find anything. So how are they going to know to find alpha as a thing to cause things to fade out? Well, if you go to Google, then it turns out that people often have asked this question in news groups, and somebody has answered, oh, well, And so Google turned out to be a really good way of solving this vocabulary problem. And most of the things that you find with Google are questions, and sometimes with the answers. And often that turns out to be a really effective way. But of course, a lot of irrelevant stuff is returned too. Even if you had a great search tool, you're still going to get all this irrelevant stuff. And there are also multiple methods. Even if you got exactly have really high precision, there are really 3 or 4 different ways of doing time that all are perfectly appropriate in Visual Basic. Which one's right for me? A lot of it depends on your context, and so people want to use examples. And so our idea is to use the context of what you're trying to program and some more elaborate techniques to try and use Google as a way of identifying exactly what kind of information, what kind of examples should be returned. And so that's something Jeff is just starting to work on. Now, in terms of making a new programming environment, we want to keep track of lots of stuff in order to make the Y-line work and this working set stuff work. And it turns out that it's very hard to keep track of that kind of things if you have a plain text editor like the Visual Studio text editor. Because even though it can do some things like highlighting and it can do incremental parsing, as soon as there's a typo, or as soon as you type a single character such that the parse fails, it has to throw away and lose all sorts of information because now it doesn't really know where the code is anymore. So we were wondering in Alice, on the other hand, you can keep track of everything. And it does all this great stuff about eliminating syntax errors and things like that. But it's been known for 40 years, since the beginning of when people started first trying to make structured editors, that although they can be really good for creating code, and you can get professional programmers to create code at enormous rates with tools like this, they're really abysmal for maintenance. And of course, most of the time it's really maintenance. So is there any way of finding something in the middle that combines the advantages of both plain text editing and fully structured editing? Well, no one's really succeeded at that. Why don't we do a real low-level study to see when people are editing, when professionals, experts are editing code, what do they do? And so we did this very detailed level analysis of 700 minutes of people programming in Eclipse with Java, 2,700 individual text edits. And there is, in fact, a lot of structure that people use when they're doing this editing. And the full flexibility of free text editing is not necessarily required even for expert programmers when they're editing code. Certain cases you do need full flexibility, so people love to edit their names into other names, and they want to do all sorts of stuff there. That's pretty easy to support. They often will use text editing operations to wrap and unwrap code. I want this in the loop, and I want it out of the loop, things like that. So we have to be able to support that really easily, which structured editors make very difficult. I want to move 3 of these 4 elements into a loop. How do you do that? But people rarely text edited across structure boundaries. People just don't edit their whiles and the ifs, which was kind of the fundamental thing that people were wondering about in structured editors. And if you have an easy way of doing this, then maybe you don't have to do that because they can just make a while and move all the code they want to in there. 98% of selections obeyed structural boundaries. People almost never selected a piece of the when and a piece of the if. They followed it, and part of the same thing and tried to do some weird editing with that. So there is a lot of structure in the way people edit code. And maybe we can use that as a way of creating a new editor. And that's kind of what Andy is doing now, is thinking about interaction techniques that take advantage of what we can in terms of the way people edit, make some operations even faster than they are now. If you want to move some code, why not have that as a single operation if that's so fundamental? And then really be able to preserve some of the advantages of structured editing. So I think this is going to be a really interesting thing. Andy's working on that this summer. So let's put all this together in a new programming environment. The goal will be to make it significantly more effective and productive for programming, both for professional programmers, novice programmers, I guess this is all, and end-user programmers. Okay? What do they have in common? What do they need that's different? We'll use this semi-structured text editing. We'll think about all these barriers to learning and ways to remove those, so that'll make it better for beginners, but also for novices in terms of learning new APIs and things like that. We'll have built-in support for working sets, so that as you're trying to do maintenance tasks, it'll be easier. Obviously, we'll put in the Y-line. We have a bunch of other ideas that we've come up with in terms of copy and paste and other kinds of tools that we think will be useful. And I think it'll be really exciting. So hopefully I'll be able to come back and tell you about all the cool things we've done in the environment. So in summary, I think there's no way we would have come up with a lot of these ideas or these tools if we hadn't done these really detailed studies of programmers and novices in advance. And so doing these studies first provides lots of new insights, lots of new knowledge that otherwise we wouldn't have. And so it's really a very effective way of getting ideas. But it is very laborious. I mean, it has taken us, hours and hours of analysis of hours and hours of tape to come up with it. What we are able to see what people really do, which is very different from what they say they do, or if you ask them what they're doing, or what their problems are, what they'll tell you. So this really goes back to the HCI principles. We're always teaching our students at CMU that it's not sufficient just to ask people what they want. You'll get good marketing data from that, but if you observe them, then you'll really find out what they really need. And that's really what we're focusing on here. We really think that our new designs are going to be more effective for all these groups, but of course, we definitely will be doing the studies to try and detail the actual improvements we get, and won't be just randomly claiming that it's better without the actual data to back it up. But we certainly will expect to, we're hoping we'll get dramatic results like we did for the Y-line, where we're getting really big numbers in terms of productivity. And that's all. Thank you.
Are there any patterns that you saw in the discrepancies between what people told you they did or told you they would do and what you actually saw them doing?
Well, we didn't even bother to ask people what they were doing. I mean, we had people, doing talk aloud, think aloud protocols. And so what they say they're doing minute to minute was very useful. Oh, I'm looking for this bug. Oh, I want to know why this didn't happen. And so that's, in the initial study, how we knew that almost all their questions were why questions and why not questions. Otherwise, we wouldn't necessarily have known what they were going at. But the point is that if you ask a programmer to think back, what was a hard thing to debug, or what do you need out of your programming environment? They're going to tell you this, hard bug they had that, took them a week to debug, 2 years ago. And sure enough, that'd, be great if the programming environment helped with that. But, what have they done in the last 2 years, and it's taken 35% of their time? That's not something that people really introspect about. It kind of goes to the old mantra that, and I think some of the other students were really, or Mary, you were looking at this, right? That if people that hard mental operations seem like they take a long time, and all this clicking around doesn't seem like it takes any time at all. So, if people have a really hard mental task, they're going to think that takes them a long time. But in fact, they're really wasting all their time clicking around. And so if you just ask people, what was hard about that, they're going to tell you what took them a long time to figure out. And, that'd be great to fix. That was some of the design problems, give them better tools. But if you really want to make them more productive, make the rest of the stuff go away so they can spend more time doing these design problems.
So you're here at Microsoft, you've got the ear of people who can start to take some measurements in software.
Yeah, that'd be great.
The IDs and so on and so forth. Has a list been composed of the kinds of operations that would be helpful for us to measure? Yeah,
definitely. the papers about the studies, go into somewhat detail, and I'd be delighted to give you more detail about what we encoded, the minute-by-minute operations on. And to the extent that those could be detected automatically, it'd be a whole lot better than detecting them from, videos, because that was really laborious. And so I think there's a lot of things that can be recorded. That would be useful. You turn on recording and have somebody do a task or measure it over a long period of time. Because I think, one of the obvious criticisms of this that, I certainly resonate to is, well, you just did lab studies. How does this really apply to somebody doing a 10,000 or a million line program? And we just say, well, we think it does, but we're not sure. So, to the extent that Rob or you guys have data that really backs us up and says, yeah, it's the same thing, even though you're dealing with a 10,000 line program, when you're fixing an individual bug, it's really only 50 lines you have to deal with right now. That would be really useful. Or, it really is a dramatically different thing. And so you have to take this into account when you're doing something. It's a new design. So if that was the case, we'd certainly want to know about that in advance.
When is Andy graduating?
He's not expecting to graduate for 2 years, so about 2 years from now. Because, a lot of, so we have this HCI program, and there's a whole bunch of students who are who are in the first class to graduate, will probably graduate next year. So he was thinking about it, but decided he really wants to make a really comprehensive tool and then test it, and it's really not likely that will happen in a year. So, yeah, Andy's a real superstar, and I think we're going to see some really exciting tools as a result.
Did you look at all at using natural language for things like asking questions for the line or navigation through code?
Yeah, that's a really important point, is that we did not, we definitely didn't want to go, to natural language. That, obviously what people want to say is, make Pac-Man, eat the big dot when he runs over it. And well, if you could just say that, then you wouldn't need all this programming, right? Or, you want to have natural language questions too. And so we're not really doing AI as part of this project, so we didn't really want to go that route. So the question was, how can we put things in the Y line that'll be clear? And luckily, and I guess this goes to your question a little bit too, in the Alice environment, all the method names had very well-designed names. The methods had real well-designed names. So all we had to do was put the methods in the menus. And people knew immediately what they wanted to do. Why didn't pack move? Well, we didn't have to say that. We just said, why didn't the pack move to method be called, basically. And so that worked out really well. In a language with more obscure naming conventions, it might be more interesting to think about what has to go in the menu to make it clear what you're asking about.
What do we expect the Y line to do in the cases where pack resize occurs in multiple places in the code, and the Y line says, oh, why didn't pack resize?
Yeah, so currently it just asks about the last occurrence. But obviously that's not nearly good enough in an environment where something happens 10,000 times and one of them is wrong. And there's other work around CMU with Mary Shaw and my former student Rob Miller, who's looking at anomalous behaviors. And can you automatically identify behaviors that are different for some reason? And that would make a lot of sense to embed that in this, that if something happened a whole bunch of times, you combine them into this big group that happened with 0 and this other big group that happened with 1, or false and true or something like that. We haven't really done much with clustering, but that would make a lot of sense to do for some things that are happen a lot of different times.
I could also see scenarios where there are cases where pack tried to resize to smaller, and that didn't happen. Yet pack resize to larger did happen. So
right.
Pack resize wound up being in the Y and the Y not.
Well, that often happens. Well, in fact, that always happens, because everything in the did menu also goes in the didn't menu. Just because we found so often people would think stuff that didn't happen and actually did. And you saw that twice. Those were real scenarios, by the way, taken from our log. You see that all the time. Surprisingly, there were no false propositions of people thinking something did happen that didn't. So that we didn't have to put the didn't stuff in the did menu. Right? Yeah, I think that's one of many, many questions that we'll have to deal with when we try and scale this up to professional environments.
So in your study of people fixing bugs in that paint program, you didn't really say too much about the effect that the interruptions every 3 minutes had on programmers.
Mm-hmm.
What were the big bullet results there?
The interruptions were designed such that you could not respond to them. So it's more like an IM that you could answer if you wanted to, but you didn't have to, unlike like the phone or something. And so we definitely saw people trying to delay their answering it, but they got a lot of money if they answered the questions right. So there was a big motivation to answer the interruptions. It was designed, to make that. I think you got you could really lose a lot of money by not answering any questions. So they were motivated to answer the question. And they were hard mental operations, so that would completely clear out your, working memory. Basically it was doing a 2-digit multiplication problem in your head. People would try a lot of interesting strategies in terms of maintaining where they were. So they'd put, the selection in the code, they put, bad text in the code so that the compiler would fail on it. They would try and mark, the code so that they would remember what they were doing. So a lot of the strategies like this, we really want to support in the environment to help people, regain their working set, basically retain what they were doing. James Fogarty's results were that people would try, when they were in the middle of an editing operation, they would try and wait until they were done with it. Or if they were scrolling to find something, they'd finish finding it and then accept the interruption. So they would often delay by 30 seconds or so until they had finished whatever mental operation they were in progress on. And so, that's mainly what James was looking for is, can we detect automatically, and, that would be possible, actually. He discovered that was the Kai paper, that, in fact, a lot of the stuff that you need to know when would be a good time to interrupt is available to the programming environment itself. Because it's, when you're scrolling, when you're text editing, things like that.
But you must have seen things where people would delay in order to, say, finish a find that they were doing.
Yeah,
and
exactly.
They'd interrupt. And then they'd come back and they'd say, now, why did I try to find this thing again? What do I want to do with it?
Right.
Right, because they'd have blown out their short-term memory.
Exactly. And so we're, I don't exactly remember all the details of that, but there are definitely some things that we think we could put into the programming environment to help with, some things about what you're doing now.
Do you have a feel for how much more productive they would have been if they took interruptions? Or did anyone do that? Was it measured?
Well, we certainly know, I think there's a measure certainly of how much time they spent in the interruptions, and I think there's a measure of how much time it took them to get restarted.
Oh, really?
But I don't remember it offhand. If it's not
control group with no interruption.
No, we didn't do that. Yeah, it probably, given the small data sets, it probably wouldn't have been, statistically significant, the differences between the two groups. Just my intuition. But, that would be an interesting study to run. Okay. Thanks. Oh, thanks.
Have you talked about a change management? Do you know about